Okay, today what we're going to do is prove the Soundness Lemma and the Soundness Theorem for our trees and show that our tree argument truly is a sound and complete argument, therefore meaning it's a valid form of reasoning. And before we get into it, I just want to point out, I think that this proof for the Soundness Lemma and the Soundness Theorem, it's pretty elegant. And I'm speaking to the non-math majors out there, whether you're just a logic student or maybe one of my friends watching this video. I hope they'll sit through it entirely and gain some kind of appreciation for how we can use proofs to prove these claims that we make and like how cool it really can be, because we do this in math all the time. But with that said, let's get into the Soundness Lemma. So I have some reminders on screen. So the Soundness Theorem is that thing written in parentheses. If sigma syntactically entails A, then sigma semantically entails A. That's what we're going to try to prove today. And then I also included these definitions because we're going to use them. And I didn't include them at the beginning of the video last time, and I felt like I probably should have. So just as a reminder, sigma syntactically entails A if and only if the tree for sigma not A closes. Also, sigma semantically entails A if and only if there is no evaluation V or interpretation, I've been using those words interchangeably, such that V of sigma equals 1 and V of A equals 0. We're going to use both of these in our Soundness Theorem proof. Okay, so we want to do the Soundness Lemma because we need that for the theorem. But before the Soundness Lemma, I need to provide a definition. So why don't we write this in a different color? Let's go. I hope everybody likes yellow. Yeah, so we're going to provide a definition real quick. So we're going to talk about what it means for an interpretation V to be faithful to a branch. So what we're going to say is an interpretation V is faithful. This is our keyword that we're defining. We've never talked about this before. An interpretation V is faithful to some branch, call it B, to a branch B, if and only if. That's what IFF means. It's just shorthand for saying if and only if. So like our material equivalence biconditional statement. So an interpretation V is faithful to a branch B if and only if V makes all sentences on B true. Now this is crucial for our Soundness Lemma proof. So why don't we write out the Soundness Lemma? So I'm going to actually just write this all out and then we'll cut back to it. Okay, so here is what we are going to prove, the Soundness Lemma. So I claim, suppose V is faithful to some initial branch B. So that interpretation V is going to make all sentences on that branch B true. Now suppose a rule of inference is applied to B. I claim that V is faithful to at least one continuation of B. Now, last time in the completeness video, we did a proof by induction for the completeness lemma. For the Soundness Lemma, it's just a direct proof. And you notice how I say suppose a rule of inference is applied to B. That means if you write out the complete proof of the Soundness Lemma, you need to go through every single case, all of our rules of inference. So conjunction, disjunction, negation, conditional, biconditional, right? And like last time, we're not going to write out the entire proof. We'll just do one case, because if you're ever asked to do this on a test that's timed, I highly doubt you'll be asked to do all the cases. And even if you are, it's pretty straightforward. Once you see the example for one case, I would bet on your ability to do all the other cases by yourself. So let's get into it. Now, this time I'm not going to cut. We're going to do the proof together. And we are going to look at the case for conjunction. So let's just scroll down a little bit. And let's switch up colors. Let's use yellow. So here is our proof. Okay, so this is a lot of words, and well, it's not a ton. But case 1, right? Let's just pretend as if we were actually going to go through and do everything. So case 1. We have to start by assuming V is faithful to some initial branch B. Assume V is faithful to some initial branch B. So that is our assumption. Great. Now, what does that mean? well, first we have to clarify what case we're doing, right? So in this case, oh, that's not the word case. In this case, we're going to suppose the suppose the rule of inference, for conjunction is applied to a sentence. As I'm writing this out, I realize how short this proof actually is applied to a sentence phi and psi on B. Remember them from the completeness video? If you haven't watched that, I highly recommend you watch that first. Yeah. So we're, in this case, suppose the rule of inference for conjunction is applied to a sentence phi and psi on B, right? So what does that mean with our trees? Remember, that just means if we have a sentence like phi and psi, we just draw a branch down and stack phi and psi on top of each other, right? That's what I mean by applying rule of inference. It'd be the same thing like if we had phi or psi. Remember, we would just put phi on one branch and then psi on the other. So that's what I'm talking about. So, but we're doing the one for conjunction. So assume that that's applied to a sentence phi and psi on B, right? So the continuation, let me see, the continuation of B will have phi psi on it, right? Just as I demonstrated. Since V, now this is where our definition is important, since V is faithful to phi and psi, then we know that the interpretation of phi and psi is equal to 1, right? This is a true sentence because V was faithful to the initial branch B, which had phi and psi on it, right? So we can conclude it must be the case that V of phi is equal to 1 and V of psi is equal to 1, right? Because that has to be the case. Otherwise, V of phi and psi would not be equal to 1. So we can conclude this. Therefore, V is faithful to the continuation of B. And that's exactly what we wanted to prove. We wanted to show that if V is faithful to some initial branch V, that when we suppose that a rule of inference has been applied, V will be faithful to at least one continuation of B. And hopefully you could see how you would argue this for the other cases, right? If you have a disjunction that's true, well, it must be the case that, phi or psi is true. So V will still be faithful to the continuation of B where at least one of those is true, and so on for all the other rules of inference. It's really not that difficult, I don't think. But now that we've done the Soundness Lemma, we want to do the Soundness Theorem. So remember, theorem, we're going to go back up, that we aim to prove is if sigma syntactically entails A, then sigma semantically entails A. Now, like we did with the completeness theorem, it's much easier to do a proof by contrapositive. So that means instead of doing the proof directly, what we will show is that if sigma does not semantically entail A, then it does not syntactically entail A. And that is logically equivalent to proving that if sigma syntactically entails A, then sigma semantically entails A. So let's get started and write out this proof. And this proof is not going to be crazy. It's really maybe like a sentence longer than our Soundness Lemma. So, Soundness Theorem. We'll show, and it's important to state this, right? To show that we're going to do a contrapositive. So we'll show that if sigma does not semantically entail A, then sigma does not syntactically entail A. So with that said, assume sigma does not semantically entail A. Now, what does that mean? Where can we go from here? Well, if we recall our definitions from all the way up here, sigma semantically entails A if and only if there is no valuation such that V of sigma equals 1 and V of A equals 0. We're saying that it does not semantically entail A, meaning that there is a valuation such that v of sigma is 1 and v of a equals 0. So let's see where that takes us. Thus, there is evaluation v such that v of sigma is equal to 1 and v of a is equal to 0. What does it mean if v of a equals 0? Well, that means that v of not a would be equal to 1, right? So then it follows, this is pretty clever. It follows then that v is faithful. This is our definition for faithful coming back, that v is faithful to the initial branch for sigma not a, right? Because sigma, the valuation of sigma will be 1 and the valuation of not a will be 1. So all sentences on this tree are true with the interpretation v. So now we're going to bring in our soundness, right? Our soundness lemma. So now, suppose a rule of inference is applied to this branch B, right? It's applied to B. I didn't specify that B was this branch. I didn't write it down. I said it out loud. The branch sigma not A will be B. So now suppose a rule of inference is applied to B. By the soundness lemma, V is faithful to at least one continuation of B. Now, Now, we've done all that, but let's not forget where we're trying to go, right? We want to show that sigma does not syntactically entail A. Well, what does that mean? Let's look at our definitions, right? Sigma syntactically entails A if and only if the tree for sigma not A closes. Well, we want to show that sigma does not syntactically entail A, so we want to show that the tree for sigma not A remains open. Okay, so that's our goal. We want to show that that tree will remain open. So we have that V is faithful to at least one continuation of B. Now what? We'll say keep applying rules of inference, and so on, right? So we'll just apply, rinse and repeat for as long as we can. So we'll do this, and so on, until the tree stops growing. Again, right? By the soundness lemma, we know there is a complete branch. There is a complete branch B that V is faithful to, right? So V is faithful to a complete branch. We cannot apply any more rules of inference. What does that mean? Well, that means that everything on that, remember, it being faithful means that every sentence on that branch is true. So we know that there won't be some sentence, call it P, such that P and not P is on B, on that branch B. So behind the soundness lemma, we know there's a complete branch B that V is faithful to. So we know there is not some sentence P, right? We'll just call it P, such that P and not P is on B. Otherwise, V would not be faithful to P. So B is open. That means that the tree doesn't close, right? Well, if the tree doesn't close, what can we conclude? We can conclude that sigma does not syntactically entail A. And that is the proof of the soundness theorem. So there you go. That's all we're going to do for today. If you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.